Hello, curious minds, and welcome to a journey into one of the most perplexing, reality-bending, and downright weird phenomenon in the entire universe, quantum entanglement. Today, we are peeling back the layers of a mystery that shook the very foundations of physics, a concept so bizarre that it led the great Albert Einstein to coin one of the most famous phrases in science: spooky action at a distance. So, what is this cosmic ghost story that so haunted the man who redefined space and time? Imagine you have a special process that creates two particles, let's say two electrons, at the same time and in the same place. They are born as a pair, intrinsically linked. Now, let's separate them. We send one electron to the other side of the room and the other electron to the far side of the galaxy, light years away. According to the laws of quantum mechanics, these two particles remain a single, unified system. They are entangled. This means that a property of one particle, like its spin, a quantum version of angular momentum which can be measured as either up or down, is perfectly correlated with the spin of its partner. If you measure the spin of the electron here on Earth and find it to be up, you will know in that exact same instant that its partner trillions of miles away has a spin of down. Not a second later, not a minute later, instantaneously. This is where the spookiness begins. This instantaneous connection seemed to Einstein to be a flagrant violation of his own theory of special relativity. A cornerstone of his work is the universal speed limit. Nothing, absolutely nothing, can travel faster than the speed of light, information included. Yet here was a theory suggesting that the act of measuring a particle on Earth could transmit information, the result of the measurement, to its twin across the galaxy faster than light. It was as if the universe had a secret instantaneous messaging service that was off limits to everything else. This deeply troubled Einstein. He believed in a universe that was orderly, predictable, and crucially, the principle of local realism. Let's break that down. Locality means that an object can only be influenced by its immediate surroundings. A billiard ball moves because another ball hits it, not because a ball on a different table moves. Realism means that objects have definite properties that exist whether we are looking at them or not. A planet has a definite position and mass even if no one is observing it. Quantum entanglement seemed to tear both of these intuitive ideas apart. It suggested that a particle's properties weren't real until measured and that it could be influenced by an event happening light years away. To formalize his objection, in 1935, Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, published a famous paper outlining what became known as the EPR paradox. Their argument wasn't that quantum mechanics was wrong, but that it must be incomplete. There had to be a more sensible classical explanation. Their proposed solution was the idea of hidden variables. Think of it like this. Imagine you have a pair of gloves. You put the left glove in one box and the right glove in another. You shuffle the boxes and mail one to your friend in Tokyo and keep one in New York. When you open your box and find the left glove, you instantly know your friend has the right one. There's no spooky communication. The information about which glove was in which box was determined or hidden from the very beginning. Einstein believed entangled particles were just like this. They carried a secret set of instructions from their creation that predetermined the outcome of any future measurement. The correlation was always there, we just didn't know it until we looked. This was a battle for the very soul of reality. Was the universe a clockwork machine with hidden gears, as Einstein believed, or was it a hazy, probabilistic casino, as his rival Niels Bohr and the other quantum pioneers argued? So, for decades, the world of physics was split. Was Einstein right? Was entanglement just a clever illusion, a cosmic magic trick explained by hidden variables we hadn't yet discovered? Or was reality truly as spooky as quantum mechanics claimed? The question remained a philosophical debate until 1964, when a physicist named John Stuart Bell devised a brilliant theoretical test. Bell created a mathematical inequality, a sort of celestial rulebook. He proved that if Einstein's hidden variables were real and the universe was fundamentally local, then the correlations between measurements on entangled particles could only be so strong. They had to fall below a certain statistical limit. However, if quantum mechanics was correct and the connection was genuinely spooky and non-local, then the correlations would be stronger, violating Bell's inequality. It was a direct challenge: perform the experiment and let the universe answer. And in the 1970s and 80s, physicists like John Clauser and Elaine Aspect did just that. They created pairs of entangled photons and measured their properties at different angles. The results were stunning and unequivocal. Time and time again, the experiments violated Bell's inequality, showing correlations far stronger than any local hidden variable theory could ever explain. Einstein, the titan of physics, was wrong about this one. The spooky action was real. The universe is, on a fundamental level, non-local. This discovery transformed entanglement from a philosophical headache into a powerful resource, a cornerstone of a new technological revolution. This brings us to the future, powered by spookiness. The most prominent application is in quantum computing. Your laptop or phone uses classical bits, which are like light switches, either a 0 or a 1. A quantum computer uses qubits. Thanks to a quantum property called superposition, a qubit can be a 0, a 1, or both at the same time. Now, if you entangle multiple qubits, their fates become intertwined. Measuring one qubit affects the entire entangled system. This creates an exponentially larger computational space. Instead of a computer trying one solution at a time, a quantum computer can explore a vast landscape of possibilities simultaneously. This could allow us to design new medicines by simulating molecules with perfect accuracy, create revolutionary new materials, and develop artificial intelligence far beyond our current capabilities. The other game-changing application is quantum communication. If entanglement can power supercomputers, it can also create perfectly secure communication. Imagine two individuals, let's call them Alice and Bob, who share a stream of entangled particles. They can use these particles to generate a secret cryptographic key. Here's the genius part. If an eavesdropper, Eve, tries to intercept and measure one of the particles to steal the key, the very act of her measurement will instantly disturb its entangled partner. The laws of quantum mechanics make it impossible to observe a quantum system without changing it. Alice and Bob will immediately see that the correlation in their particles has been broken, alerting them that their channel is compromised. They can simply discard that key and generate a new one. It's an encryption system with a burglar alarm built in by the fundamental laws of nature, making it theoretically unhackable. Ultimately, quantum entanglement forces us to abandon our comfortable classical intuitions of the world. It suggests that the universe is not a collection of isolated objects, but a profoundly interconnected web. It blurs the line between cause and effect, between here and there. It reveals a universe that is fundamentally holistic, a cosmic network where the separation between 2 points might just be an illusion of our limited human perspective. So, what's your biggest question about quantum entanglement? Let us know in the comments. Subscribe for more deep dives and see you in the next one.